Good morning, class. This is the instructor for Physics 2, basically. This is in response to a question that Aaron asked, and it has to do with problem 51 from chapter 27. So I want to share this discussion with everybody, and please, if you have any questions like that, do ask them in the discussion board, and anybody else can interfere. But this one is from problem 51, which is part actually of the homework. So I want you guys to see how that can be answered without really having to do a lot of physics. But of course, we have to do physics at the end, try to understand what's going on. Anyway, basically what the problem basically states is that, look, you have a particle that is, at some point it was moving in a direction called V1. So in this direction, V1, which is making, according to the problem, an angle of 45 degrees with respect to the x-axis in the plane xy. And at some point it was moving completely in the z direction and with velocity v2. Note that v1 and v2 in magnitude are the same, with the same magnitude from this problem. So therefore, the magnitude of the velocities are the same, except that the direction changes. And it's all of it is inside the magnetic field, and of course we're tasked to find what the magnetic field is. The measurement for the force in this case is, it turns out that F1, once we measured it, was completely along the negative x-axis. And when it was moving parallel to the z-axis of the velocity v2, the force that was measured, F2, was completely in the x direction, the positive x direction. So that's basically what we're given, and what we're asked to do in this case, what are the magnitude of the magnetic field in terms of the charge Q, and the charge Q is assumed positive, so that's a critical piece of information, and V1, which is the same magnitude as V2, and F2. Finally, they want to know what is the relationship between these two forces, F1 and F2. Okay, so what I did in here is basically I am taking the general vector of components B1 and B2 and B3 along the X and Y and Z directions. At this point, I have no idea what B1 and B2 and B3 are with respect to one another, or in terms of these quantities that were given to us, Q and B1 and F2. All I know is that this is a vector in 3D, has three components along the X and Y and Z directions. Now, I know from the problem that the velocity V1 is making an angle. I'm taking a general case of angle theta here because we will try to understand what's going on with this angle theta. With respect to the x-axis, of course, V1 has no component along the z direction because it's in the xy plane. So in this case, its components are easily, you can see from the projection of this vector, V1 cosine theta and V2 sin theta along the x and y directions. It has no component along the z direction. Now, the vector V2 has the same magnitude as V1. That's why I put it in here as V1. And it has no components along the x and y direction except along the z direction. And that is V1, basically. That's the whole vector itself along the z direction. The force F1 from the schematic that you can see in here and from the information that was given to us in the problem is along the y direction. So we don't have to worry about that one too. The components for F1 are F1. Of course, that's the total vector, 0, 0, and negative 1 because it's in the negative z direction. F2 is given to be completely in the x direction. Its magnitude is F2 and its components are 1, 0, 0. So basically, based on that and the fact that the forces are just a cross product of the velocity and the magnetic field B times the scalar Q, and Q is positive, so everything doesn't change in terms of the sign as far as Q is concerned. It's just a number, and a positive number, that is. So all I have to do now is just model this scalar product with all of the information that I have and equate component by component. That's basically how two vectors are equal to one another if their respective components are the same. So having said that, this is from one side what F1 looks like. That's from the information that I have upstairs there from the problem that I stated. And the cross product in here as a format, of course, I have in the x direction, I have sine theta times b3 minus 0 times b2. That's why I wrote in here b3 sine theta. For the j component, it's cosine theta times b3 minus 0, but of course I have to multiply by negative 1. That's why you see a negative b3 times cosine theta. And the z component has these two products, b2 cosine theta minus b1 sine theta. That is basically how this vector is formed. So this is now a vector. The components, when matched together, 0 equals to b3 times sine theta times qv1 times f1 on the other side. But it doesn't matter. The only solution for that is b3 equal to 0. That's what makes this one 0, and that's what makes this one also 0. Because theta is definitely not, theta is 45 degrees. So in this case, these numbers are not 0. So the only way that this could be 0 is for b3 to be 0. So b3 is 0. So the vector that we started with having 3 components, we know one of its components now is 0. So it has no z component. So the magnetic field cannot exist in the z direction. For one reason is because F1 is already in the z direction. So you can argue, say, hey, magnetic field cannot be in the z direction because the force is a result of V crossed with B. And if B has is actually along the z direction, then we have no component in here for F1, which is purely along that direction. So that fixes B3 at least. So we still have to deal with B1 and B2. Well, we go to F2. F2 is given by that vector again, that as I just stated in here, just put it based on the information that was given to me. F2 times, which is a vector with only components along the x direction, is QV1. And then I am forming the cross product in here based on V2 now, and V2 is given to me as being V1 in magnitude, but a vector that is completely in the z direction. So having said that, then I do my cross product. Again, I put vector V first, and the vector B, now knowing B3 is equal to 0, so that simplifies the algebra a lot. So this I have 3 equations. In the x direction, I have F2 on one side. On the other side, I have QV1 times 0 squared minus B2 times 1. So I have minus QV1 B2. And then in the z direction, in the x direction, I have, and the y direction, I have 0 on one side equals to 0 times 0. No, I'm sorry. What am I saying in here? I should have done, yeah, that's fine. 0 times 0, I think this equation is for the z direction. For the z direction, I have 0, and on the other side, I have 0 times b2 minus 0 times b1. So this is the actual equation for the z direction. For the y direction, I have 0 squared minus b1 times 1. But again, I have to flip the sign in here, so that's why I see b1 times 1, or b1 at the end, equals to 0. It doesn't matter. So that's B1 also is 0. So this vector now has no x component and has no z component. So the only component that remains is the component along the z direction, the y direction, which means that at the end, this is the only equation that survives for the magnetic field. And the magnetic field, once I solve this equation, because B1 and B3 are 0, so the only thing that remains is B2 given by minus F2 over QV1. And the minus in here means that the magnetic field must be pointing in the negative direction in the y-axis. And that is critical because you can see from this one in here, that makes sense. Because if I have V in the z direction, B in the negative y direction, the force according to the right-hand rule, and you can point your right-hand rule with V pointing toward the z direction, and the pointing finger pointing down, and you will see that the resultant vector is going to be in the positive x direction. So that makes sense perfectly, at least in terms of the right-hand rule now. So that's what the negative sign is. So the magnitude of the vector B is itself is just F2 over QV1. So that answers that question about the magnitude of the vector. Now, if I go back to the other expression with the that we found earlier, namely the fact that, what is that? So we found this one in here, and there was another relationship that we found to begin with. No, we didn't express it, but it's in here, okay? Negative F1 times 1 in the z direction is equal to B2 times cosine theta minus 0, because B1 is 0. So it's have basically B2 cosine theta times QV1 is equal to negative F1, but I know QV1 times B2 is, for this expression, negative F2. So from there, basically, I have F1 and F2 related to one another this way. And that's basically what the answer to this problem is. I mean, it's simple algebra. I hope you guys see that in this case. I didn't try this expression, but it's very simple to see. From this expression here, 1 times F1 with a negative sign is the Z component. With B1 equal to 0, we just solved it earlier, in the previous steps, it is B1 is equal to 0. Then I'm left with B2, and B2 is equal to negative F2 over QV1, and QV1 cancels this one, so I'm left with F2 times cosine theta with a negative sign coming from this negative sign is equal to F1, basically with a negative sign. The negative cancels the negative, and everything else basically settles to the fact that these two forces are related to one another this way. It's interesting. I know theta is given 45 degrees for this problem, but what if theta is equal to, let's say, 90 degrees? If theta is 90 degrees, as you can see from this schematic, it's going to be along the y direction. And if the velocity is along the y direction, either moving up or down in this case, if it's going up with a 90-degree direction or negative 90 degrees going down, the force should be 0. Why is it 0? Because remember, you have V cross B, and B is already in the y direction, so if you put B along the y direction, there should be no force. So, and I guess the general discussion that force F1 should be less than F2 because of the fact that this is the maximum force you're going to produce in this direction, and that's basically what that is. I hope this helps.